Hi everyone, my name is Tovio Roberts, and this is another Galvanize study hall. You might notice that in the description it says we're starting at break continue pass, which is not true. So I'm just going to grab the actual link. I know on Friday Clark went over dictionary accumulators, and I'm going to spend a little more time on dictionary accumulators because it is such an important thing. I updated the link, and I'll also update it in the chat, even though chat is disabled. I'll just throw it into the thread. So we're starting off with, there's a question. If we are to simulate an experiment using a certain number of samples, would we use the PMF or CDF function? This is in reference to the mock geometric interview, and there's some code attached. So I'm just going to grab that code. And let's say we have, so I'm looking through this. And this is just a direct question for a student who's asking. Okay, we've got the sample counts, we've got the probability of a given success, we've got the min, the max, and the number of samples. And we're going to go from k value from ranging from the min to the max plus 1. And then we're rounding. Well, here I would use... depending on how the question is asked, here I would actually use the geometric PMF. So, yeah, I would use the geometric PMF here because we're going to get a probability of an occurrence of k, right? And then if we're reproducing this, if we're observing over and over again, you know, num samples times, right? Let's say this is 10,000 times. If we're observing this over and over again. Also, do you mind just pasting in your geometric PMF function really quick while I'm explaining this? So if we're doing this over and over again, we're getting a probability out of the geometric PMF, and then we're multiplying that by the number of samples, right? If we were to do this with the CDF, it would be a little more difficult to explain, I think, right? If we're talking about the geometric PMF, basically we're saying what is the probability of this many failures before the first success, or this many failures including the first success, and you know, it would be like asking, this function would be like allowing us to answer the question, well, how many times, if we've observed this 1,000 or let's say 10,000 times, how many times would we expect to see k trials, right? Not the probability of k trials, but how many times would we expect to see k trials? If we were using the CDF here, we'd be answering a different question. We'd be answering the question, how many times would we expect, less than k, or k trials or less, right? And so that cumulative approach, there's nothing wrong with it by any means, but it's a little harder to explain, and it's harder to, in my mind, a little harder to come up with a situation where that's what we would want in terms of sample counts. I would think we would want sample counts showing, just the probability of k counts, right? K trials. Sorry, the probability of k trials before the first success, or up to and including the first success, however you want to write the geometric PMF. I would think we would just want that probability multiplied by the number of times we're, making this observation, right? That would give us our expectation. So yeah, the only thing I would change here in your code is switch this from the geometric CDF to the geometric PMF. Otherwise, this looks fine. Yeah, this looks fine to me. And I'm assuming you're using the exclusive form of the geometric PMF because your K is starting at 0. Oh, yeah, because your K is starting at 0. Yeah, hope that answers your question. I'm going to jump over to something completely different that is maybe more, back over on the Learn materials. So I said I was gonna talk dictionary accumulators here, and part of the way I'm going to talk about this is through analyzing the outcomes from a polynomial function. So there's this lesson, parallel list. This is in accumulators, I believe. And I just recorded a video for just explaining this parallel iteration with enumerate. And it's a pretty straightforward idea, but I think some people have been confused because of the mathematical language here. So in the video, I just go through and explain this function right here. I'm just going to grab this function for our purposes, and I'll talk through it again. Essentially, we are going to have a polynomial in some form, right? We're going to have a polynomial, and I'll just say that it looks like something like this. So 5x to the, not 5x, but 5 times x, right? 5 times x raised to the 5th plus 4 times x. Well, I won't do 4 here. Let me do 2 times x raised to the 4th plus, let's say, x, right? This is actually 1 times x raised to the 3rd plus, I don't know, 12 times x squared plus another number, 6 times x to the 1st power, right? Plus, let's say 3 times x to the 0th power. And of course, that's going to be 1, right? So this is what our polynomial might look like if I were to write this. Well, let me see. If I were to write this out in a longhand way, it would look like this. So this is 5 x. Let me apologize for. It's going to look like caveman scrawl, but that's okay. 2x to the 4th plus x to the 3rd plus 12 squared. I'll just continue on the next line, plus 6x plus 3. So, this is how we might write it in Python. This is how we would represent this, right? F of x equals 5x to the 5th plus 2x to the 4th, etc. Now, x is going to be the same value, right? Oops, forgot to put an x in here. This should be 12x, right? 12x squared. So we're going to have a variable x, right? And we're just going to feed that in to our polynomial function here, right? We've got this coefficients. We've got all our coefficients here, which we can store in a list. 5 to, this is going to be a 1 right here, right? 12, 6, and 3. So why don't I just do that? I'll say, we've got some lists. It's going to be 5, 2, 1, 12, 6, and 3. And this is going to be our coefficients list. And then we're going to have a value of x. And I'll just say x is, I don't know, x is, let's do 4. So this is going to be 5 times 4 to the 5th, plus 2 times 4 to the 4th, plus x, plus 4 cubed, plus 12 times 4 squared, plus 6 times 4, plus 3, right? So that's essentially what we're talking about here. It's just we're a little more abstract here. We've got coefficient sub 0, right, which in this case would be 5, coefficient sub 1, which would be 2, sub 2, which would be 1, etc. And in the formulation here, we're considering n to be the length of our list, okay? We get n up here. It's actually the length of our coefficients list minus 1. So we're going to consider this our highest coefficient, right? This is going to be 5 times x raised to the 1, 2, 3, 4, 5, 6, raised to the 6 minus 1 minus 0, okay? Because it's the 0th index. All right, so just looking at this for index, value, and enumerate these coefficients, the result is going to get incremented by the value, right? This is 5, right, in this first instance, times x, which would be 4, raised to the n minus the index. So n at this point would be 5, right, because n initially is the length of this list minus 1. So that's 6 minus 1, which is 5. And that's going to be 5 minus the index, which is 0, right? And so that's 5x to the 5th. All right, so if I run this, let's just see what we get. Just print polynomial of the coefficient list and 4. So that gives us 5,915. Pretty simple, right? Like, I think there's a little bit of a mental gymnastic, a little logical cartwheel right here, mixed with this line 3, so line 6 and line 3. But once you get that, you could see how we might go about approaching this. Another way we could approach it is we could reverse this list, right? We could reverse it, and we could just raise it to the length minus 1. Or we could enumerate differently. We wouldn't need to do this form of enumeration. This is sort of a forward approach, but if we reversed it, right, this would be 3 times x to the 0, wouldn't it? And this would be 6 times x to the 1st, and 12 times x squared. So usually when I do this, I reverse it. But either way, it's the same function. You know what? Let me just go ahead and write this in a reversed form. Now that I've explained it this way. We're still going to use enumerate, but here what we'll do is we'll just go like this and reverse it. And instead of doing n minus I dx, well, do we even need n at this point? We actually don't. We can say for index value in enumerate, coefficients in reverse, then we can just raise it to the index. Okay, let's see if that gets us the same answer, and if it doesn't, I'll troubleshoot it. Yeah, same thing. I usually do this. It doesn't really matter which way you go. This is sort of a different mental gymnastic because you're starting at the lowest order in the polynomial, right? This just 3x to the 0 and going from right to left. I like this way a little bit more. So let's consider dictionary accumulation. And we've got this function, we've got this polynomial function, and what we can do is hold one item constant, and I'm going to hold, we can hold all items constant and vary one item. I'm going to vary x, and I'm going to hold all these coefficients constant, okay? And we're going to populate a dictionary with this. So this is going to be pretty easy. And this is just one of those many ways that you can use a dictionary accumulator. So I'm going to call this polynomial dictionary, and we're going to pass in a coefficients list, and then we're going to pass in a low x and a high x. And high x is going to be inclusive. And in this case, we're only using whole values of x. So, we could write this to do, a finer grained approach if we want. I probably wouldn't do that right now. I might do that with another function. Okay, so this is going to be, we're going to make some dictionary, right? We have some dictionary named D. And, you could name it something more meaningful. Most people are going to know what this is. So I'm going to say for x in range, and right, we don't need this x at all. For x in range, we can go from low x to high x plus 1. I want to be inclusive here. And that's, you don't always have to be inclusive, of course. Here I'm being inclusive because the implication is we're trying to see everything in this range. And I'm going to say d sub x is simply going to get this polynomial. I can copy this directly. And we're going to pass in the coefficient list. Or maybe I'll even call this coefs, just to be, sort of in line with this polynomial function up here. So I can pass in the coefficients, a low x value, a high x value, and this is as simple as saying d sub x is going to get the result of the polynomial on this varying of x. So we're going to get x at everything from low x to high x. So then we can just return d. And what I'll do here is I'll say for key value in polynomial dictionary. And I'm going to pass in this coefficient list up here. And maybe I'll just get this, just pull this down here. Okay. And so I'll pass in the coefficient list, and for my low x, I'll do -10. My high x, I'll do 10. And I have to do dot items here. And I'm going to say, I'll just print this as an f string. And I'm sure you have all seen me do this a lot of times. I'm just going to put in the key and the value here. So I can run this, and we can see, -10 gives us -479,000, right? And we can watch, we can look at the shape of this in this way. We go 10 to the left, right? Maybe I'll just draw this really quick, just a little bit. So we've got some kind of, thing, and so we go 10 to the left is way off the charts. Maybe we just imagine this is a really, really high scale. So -1 to the left is 5 down, or sorry, it's 5 up, right? So, we've got -1 and 5. 0 is 3. Let's say 3 is there. 1 is 29, which is, just way up here, probably way further. And then, 2 is even further. So we can imagine there's this line here. -1 goes up to 5, but then -2 is way down like 97. So we've got, I'm going to try to draw this. It's going to be bad. It won't be too bad, I guess. That's how mouse drawing works. And then something like this, right? And yeah, something like that. We can see this represented in the dictionary. We could use matplotlib and plot it out, actually plot it out, but we can get an idea of how this thing moves and grows. It's an order, it's an order 5 polynomial. We have the potential for a lot more curvature than we have here, but the structure of the polynomial, when we look at it, it's all additive. These are all positive values. We're going to get something probably pretty different if I put a couple negatives in here. And, if I put, let's say, 1 negative in here and run it again, and let's see what we get. So it's not that different offhand. Still a similar shape. Is that true? -1, 1.5. Shape changed a little bit, but you can start to gather that what we can see here is, varying. We can approach this and analyze a polynomial function pretty easily. We could do other things, right? We could, instead of having a low x to a high x, we could vary one of these values, and we could vary it pretty extremely. So why don't we do that? Let's say we want to vary this value. Now, that's going to be a little trickier, right? Because we're passing in the coefficients. And we would have to rethink how to do this entirely. Let me think about this for a sec. Yeah, it wouldn't be that fun to explain it. But it's not something, but it is something that's very doable. So if we wanted 0, 1, 2, 3, 4, the fourth order. I feel like I'm going to get in the weeds if I do this. We could do low fourth order to high fourth order, and then we could pass in a value of x, right? And then we would have to modify coefficients. Why don't I just do it instead of explaining it? So I'll do low fourth to high fourth, and I'll vary x. Or sorry, I won't vary x. I'll hold x constant. So maybe I'll change x to, I don't know, 7. And we'll change the fourth order as we go. So maybe for this, I'll change this to 0. Why not? It doesn't really matter because we're going to be modifying it as we go. So we're going to say for fourth in range, low fourth to high fourth plus 1. We're going to pass in polynomial coefficients of x. We've got x here, so we don't have to change that yet. But what we do want to do is change the 0 first, right? The index 1 of coefficients. So I'm going to say coefs sub 1 is going to get fourth. So small modification, but notice that we are holding a different thing constant now. We're holding everything except for this fourth order fourth order coefficient value constant. We're going to vary that now. And let's see what that does. Oh, that makes sense. We need to change the key here to fourth as well. So we're going to be taking the same polynomial, but modifying, we're changing the key, which is the value that we're putting in for fourth. So this should now go from -10 to 10, as well, it did before. But now that doesn't represent the variable value because the variable is held constant. And we get, we get something remarkably different, of course, because that x is held constant. And what we get different, the differences between these are all going to be around 2000. Is that right? Yep. And that's because, the nature of a polynomial is that it has this additive property. And so this fourth order, you can imagine we're moving by about 2000 every time we do that. Is that right? Until we get out to the ends, and then we're moving by further. Okay, so that's just a little bit of a little bit of exploration around dictionary accumulators. They're so important for the technical interview that we could probably spend a lot of time on them, and that wouldn't hurt anybody. And maybe yeah, I'm gonna move forward from here, and we'll see dictionary accumulators more. We're going to not stop seeing them. Okay. All right. So we have this section on functions, and we've been writing functions this whole time, and there is some reasoning behind why you want to do this. The biggest thing I would say here is that you want functions for making a reproducible code and making and encapsulating ideas. And the reason I say encapsulating ideas and not something like, encapsulating a procedure, you want to think of a function as being almost like a separable idea. And let me think about a good thing that we can work on as a separable idea. Oh, I know. Why don't we do this? I wrote this function before, but it's one of those functions that's really good to know. I'm going to call it find anagrams. And we'll pass in a list of words. So I'll just call this word list. And this should return a list of words that are anagrams to other words in the list. Right? It's a good function to know how to write. There's a number of ways to write this function. I'm going to write it in a very simple way. I'm going to just compare each word to each word in the list, right? So I'm going to say for word 1 in the word list, we can say for word 2 in the word list, and I'm going to say if is anagram word 1, comma word 2, then we're going to append this to a list called anagrams. So anagrams.append, we're going to just append word 1. So we need this anagrams empty list. So there's another little piece of logic I'll put in here so that we don't get duplicates, but this is fine for the moment. So what we need here is a function called isAnagram, and the job that function does is it tells you if a word is an anagram to another word. Is word 1 an anagram to word 2? Well, let's find out. So this is an idea, right? This is a separate idea from finding anagrams, or it's a dependent idea, right? Find anagrams is dependent on isAnagram, but it's sort of a more atomic idea. So it's a place where we might write a separate function, and that function, we might use it somewhere else. So it's nice to have it in its own form, but we might not. But it's still nice to have it in its own form, because when we read this line 13 that says isAnagram, what we're really saying is we don't need to know how this works. You know, we can just pass in a couple words, and it'll tell us if it's an anagram or not. So let's say if word 1 is equal to word 2, let's return false. We don't want word 1 to be equal to word 2, because cat and cat maybe technically are anagrams to each other, but they're the same order of words. So, you know, I'm just going to solve that base case or that condition first, and then I'm going to say if the sorted version of word 1 is equal to the sorted version of word 2, then we can return true. I'll just do that. Okay. So we might test this separately from find anagrams. Let's go ahead and see. So let's print isAnagram of cat and tack. And let's print isAnagram of dog and dog with 2 G's. And let's just do that. I think that's going to tell us enough. Oh, we return none here because I didn't do return false at the end. So let's try that again. True and false. I'm assuming this is what we want. I think it's going to be fine. So find anagrams takes a list. isAnagram and anagram takes 2 words. We're just separating out a more atomic function from this function, and that's generally a good practice. So I can just return anagrams here, and let's make a list. So let's make a word list. Just call it words, and let's put in act, cat, tack, dog, dog, God, frog, bear, say ear, and R. So what we would expect to get back is a list of act, cat, tack, dog, God, ear, R, and exclusion of dog with 2 G's, frog, and bear. So let's see how this does. So find anagrams of these words. I can tell you offhand that there is going to be a problem here, or there's going to be something a little logically incorrect here. We get act, cat, cat, tack, tack, dog, God. And there's a couple ways we can solve that. One way is casting this as a set and then as a list. That works. We could also exclude if the word is already in anagrams. So if word 1 not in anagrams, then we can append word 1. And notice that gets us a deduped list. So act, cat, tack, dog, god, ear, r. Yeah. So kind of the point here is we want to make atomic functions. That's really what we want to do here. Now, notice this. I made a sort of temporary docstring. This isn't a complete docstring. So, let's adapt this sort of docstring template we have here and write something a little bit better. When you encounter this in the technical interview, there are going to be a couple points where we say, hey, write a function according to the docstring. That's what we're going to ask for. You should be able to get everything you need in order to write the function out of the docstring. Okay, so find anagrams. Well, what does this do? I would say given a list of words, returns a finds all words that are anagrams to other words in the list. And the next thing I would write is return. This is going to return we can say it's anagrams. It's not completely necessary to match this in some way. Like here I'm saying it's anagrams and it's a list, but what if you were to write something that has that returns from an operation, right, as opposed to returning an actual collector or accumulator that's already been named, right? Like you might write a function that returns a the results of a comprehension, right? And that comprehension obviously has no name if it's following a return statement. But you want to have some meaningful word here, so it returns the anagrams, which is a list. And then, this is a list of the anagrams in the original word list. And I'm actually going to call this word list, right? Because that is the name of one of the parameters. And it's nice to have to follow this convention of, I think is it 72 characters? Maybe it's 71 in Python. But whatever the width is, to not exceed that width. Okay, so we only have one parameter here. We have word list as a parameter. So I'll go there. Word list is a list, right? And a short description of it, well, that's just a list containing words that may or may not be anagrams to each other, right? Containing words, maybe I would say as strings, that may or may not be anagrams to each other. Now, list, you might even do something like this, string or str. And that's just saying it's going to be a list of strings, if you know that. If you don't know that, then maybe you have to do some type checking at some point. But this is a well-formed docstring. Given this docstring, we might expect you to write a function that does this. Now, how do you write that function? There's a lot of ways to write the find anagrams function. This is a nested loop approach. This is really easy. Offhand, it compares everything to everything. There are ways to write this better than this, more computationally efficient. But the real point here is you want to be able to translate a docstring into a function. You also want to be able to author a docstring. We're not going to ask you to do that on the technical interview, but any code you write in the real world, you're going to be expected to write docstrings. That's just really part of it. Docstrings become great documentation, right? If you're trying to go through and figure out how something works. If you're just reading code, it's going to be kind of hard. And we can see this in, maybe I'll pull up sklearn, GitHub. I'll just pull this up, and we can just take a quick look. So scikit-learn is something that you're all going to use quite a lot, and I'm just going to go look at their code base on GitHub. So let's look at clustering algorithms, and let's look at Birch clustering. And notice there's at least comments for these functions, and not all of them have these well-formed docstrings, but a lot of them do. And in this case, there's a docstring for the class, which is the definition, the template for creating objects. And then not all of these, well this is an init, but all of these have some sort of documentation that is explanatory. Now, these aren't fully well formed, but the classes are. The classes are well formed docstrings, and there's documentation that can be auto-generated from these classes. And it really just depends on the culture around the project. How you write docstrings. This is how I write Python docstrings. I think it's very readable, and it's easy enough to just take a template of this, or take another docstring, copy it, and paste it in. Or if you have if you set some key commands in VS Code, it can populate a generic docstring if you want to do that at some point. Okay. So I just wrote that for find anagrams. I could write it for isAnagram, but I think you get the idea here. The main thing is you want to be able to take a docstring and translate it into code. You also want to take your code and be able to write a docstring to accompany it. We mentioned test-driven development here, and you might imagine, let's say you receive something like this. This is a function that has not been written, right? In test-driven development, what you're likely to do is write a test first, and then modify your function according to the docstring in such a way that it'll pass the test. So that kind of requires you to write a test, or write tests, and then write docstrings, and then write code. And that is a common paradigm in coding. If you're doing any kind of software development out there in the world, you're probably going to be doing some kind of test-driven development. In practice, you might see it as writing the function and then writing tests for it, which is one way that it's done. But more often you would write the tests first, and you would write your docstrings first. So I'm going to go ahead and back this up. Get the code back in there. So parameters versus arguments. This is really just a semantic thing here. Parameters. Word list here on line 10, we call this a parameter. It's waiting to get an argument. And down here, where we pass in words, we pass this in as an argument to find anagrams. Okay? So, you might ask yourself, well, why is there this difference? And I do think it is kind of semantic difference. When you call the function, you pass in an argument, like we're doing on line 40. When you define the function, this definition of the function has a parameter. And that parameter is sort of a container waiting for some data. And as a container, we don't really know what's going to go in there. And I think in that sense, there is a sort of basic difference, but at the end of the day, this parameter is waiting to hold an argument. So we've already seen default arguments a bit, and in this case, in these functions, we probably wouldn't make default arguments, to be honest, but they're pretty simple. So let's just come up with a different problem. Let's just write a really simple function here. Let's write raise to the power, and we're going to pass in x, which is the value that we are going to raise to some power, and we're going to pass in power. And we can just return x raised to the power. Now, you might be like, okay, well, why would we do that when we just have this simple operation? Yeah, you're right. You're right. This is just to demonstrate something. So what if we're thinking that we often square numbers, If we often square numbers, we might set as a default argument power to 2, right? If we're usually squaring something, then we can do that. And this is really a question of, is this going to be helpful in your code? Is this something that are you so often squaring a number that you would just want to do this by default? Well, possibly. So maybe we'll square 25. I don't explicitly have to put power gets 2 in here. I can just put in 25 because power is already set. And 25 squared is 625. So, yeah. So that's why we have a default argument here, right? So our parameter power is receiving a default argument, and we end up writing a little less code on line 6. And there's this lesson on return. This should really be a review. The main thing that I would remind you of is you can return multiple things. And, for example, we could return x and power as well. And just notice the data type that's returned. It is a tuple, as we talked about a few days ago. We get a tuple returned here. And that's convenient. It's convenient that we can do this in Python, that we can just separate these values that are being returned by commas, and it will return a tuple of those. And then when that's unpacked, we can look at them. We can unpack them individually. We can treat it as a tuple. It's just a convenience. But remember, when you're returning, you can return multiple things. And we'll definitely ask you to return multiple things in the technical interview. So there are just some other, generic concepts. The KISS concept, keep it simple, stupid. This is really about that function atomicity that I mentioned earlier, right? We separated out is anagram from find anagrams. And the reason we did that is we wanted to keep things simple. We wanted to keep things able to be navigated, right? You can read these functions and you build one idea off the other idea. If you're trying to write a huge function that does everything, you're going to probably confuse yourself with it. And yeah, coding can be tricky enough as it is without you confusing yourself in the process. So this is just a general computer science idea. Just try to keep it simple. You know, don't write optimal code generally when you don't need to even. Err on the side of it being readable, right? You want somebody to come to your code and be able to read it. So that's a good thing. Variance on KISS. Simplicity is the ultimate sophistication by Leonardo da Vinci. There's just some quotes here. I would say the really important one, which we're actually going to talk about in Premium Prep in a more substantive way, is Occam's razor. In a lot of cases in data science, you want to choose the simplest model that is as effective as any model that's more complex. You want to solve problems in the simplest ways, preferably, and often in the most explainable ways that you can, while still, you know, generally having good results of your models. So, yeah, we'll talk Occam's razor a little bit more later. But yeah, you want to be considerate of the people who are reading your code. I think that's a big part of what I'm talking about here. So args and quargs. Let's write a function called multiply all. And again, this is going to be a very simple function, but we're just going to use it to kind of explain args and quargs. So multiply all, and okay, good. If we're using Starargs, well, first let's just try this out. We're going to see how Starargs works. So, you know, we can return multiple things, but we can also pass in multiple arguments. When we pass in multiple arguments using Starargs, we're going to pass in a list, and that list, sorry, we're not going to pass in a list. We're going to pass in as many arguments as we want to the Starargs parameter, and those are going to get put in a list. So let's just to start, let's demonstrate that. So I'm going to say for item in args, let's just print the item, and let's call this function. So I'm going to call multiply all, and it's going to be 4 times 4, 8, 6, just those. And notice I don't have to print this because I'm printing from within the function, and we get 4, 8, 6, 3, 7, 5, 1. So args in here is a list, which is convenient for us because we can just use it. We can just use it as it is. So I'm going to say the product is going to start at 1 because of the identity, and we'll say we'll just increment this by each item, and maybe I'll change item to num, and we're expecting numbers in here, and then we just return the product. So this is sort of a, you know, we could pass in a whole lot of numbers, and this is going to work for us. So 20,160. Let's pass in a range. Let's do list. No, we can't do that. Yeah, okay. But that's Starargs, essentially. This comes in handy. You might not use it as much as, well, it depends on what you're doing, really. You might use it if you're writing a function that is going to take in, let's say you're trying to calculate the distance between many lists of some given dimension. You might use Starargs and pass in 4 lists and get some distance measurement between all those lists. Just as an example. That's not really different from what we're doing here, right? We're creating an accumulator, and we're increasing that accumulator by multiplication against each value in our passed in arguments. Now, Quarks is a bit different, but only a bit different. So let's do names and pets, and we'll pass in. We'll go ahead and do Quarks. So this is going to be a little different because instead of this being a list, we're going to pass in some associations, and we're going to say yeah, let's do this. Let's do names, and we'll make a list. Bob, Janet, Desmond, and we'll do pets, and pets will be some affiliated thing here. So let's do we'll just say these are pet names: Chloe, Furball, and I don't know, Stinky. And let's say these are parallel lists. If we pass these in, we can first, let's just look at Quarks and get a sense of what this looks like when we run this. Oh, names of pets got an expect keyword. Names. Oh, wait a minute. Oh, that's why. You need double stars on Quarks. There we go. So notice we get this dictionary where the names are in a list and the pets are in a parallel list. If we wanted to, let's go ahead and transform this dictionary really quick. So let's just make a dictionary that will get the values of Quarks. And we can do this a couple ways. I'm just going to do it in kind of the classic way. So for I in range, and we'll do, actually, I'm going to unpack Quarks. So I'm going to say, oh, but we want to be able to do this for an arbitrary number of values. So if we're assuming parallel lists, and let's go ahead and assume that. Let's say for I in range, and we'll say the length of Quarks. So this is going to get us 0, 1, 2 as indices. We're assuming names and pets will be available. Let's see. I think we need to do one more step here. So let's get the keys. Yeah, let's do that. So D keys is going to get the Quarks dot keys, and then we can say we can do this in a nested way. We can say for K in D keys, then for I in range, the length of Quarks sub K. I have to think about what I'm really trying to do here. I want Bob to associate with Chloe, Janet with Furball, and Desmond with Stinky. So for K and D sub keys, yeah, let's think about this in a different way. So yeah, let's say for k in d sub keys, let's just print the k. So names, pets, none. Oh, well, that makes sense. Names and pets. So those are two lists. And we can say for item in d sub k, let's go ahead and not d sub k, but Quarks sub k. Yeah, I think what I'm trying to do here is a little silly. Why don't I just go ahead and say, I think taking this parallel approach is just not actually great. Instead, what I'm going to do is make a bunch of attributes for this person. So name is Bob, pet is Chloe, and let's say car is a Datsun. And then let's just demo this and move forward. And I'll just say for kv in quargs items, let's just print these. So I'm going to print each key and associate it with its value. Yeah, and I think if I was doing that list approach, I would actually just use args. I wouldn't use quargs. I would just pass in a number of parallel lists, as opposed to the key value approach that I was taking. But that's me. Name Bob, pets Chloe, car Datsun. So this is just kind of a nice way to think about associations, right? You can pass in an arbitrary number of associations. And where I've used this the most is in shell scripting with Python, where I'll pass in a number of keyword items that are going to be used distinctly with each other, right? Like if you're trying to separate a signal based on some level of frequency, you might pass in that frequency threshold as FREQ underscore threshold, right? Right here. So frequency threshold gets and then some value. You might be passing in a sound signal as well, and might be signal gets the location of a wave file or something like that, and then your code would go grab that wave file and threshold based on the frequency that you've put in. There might be other things you want to do as well with that. You might want to add gain. You might want to normalize the sound. And all of those could be separate keywords that you only pass in if you need them. And then in your script, you would have default values. So, there are a number of ways to use quargs. I usually settle for args if it's within a function I'm writing, and unless it's a shell script. And then I'll often use quargs because then I don't have to know the order in which to supply certain items. Like I don't have to worry about the indices in args. Anyway. So it looks like we're looking at importing. Yeah, okay. Yeah, let's look at importing. Importing is something we've done a lot already. We've used random a lot. And we have this little brief statement about libraries versus modules. Let me show you a library. So pandas. Pandas is a library that has a lot of modules in it. Another one, and you're going to use pandas a lot. Matplotlib is another library, right? This is for creating visualizations. And, you know, what else? What else? There's so many. NumPy is a library that you're going to use quite a bit. There's so many of these. These are big collections of modules. And, you know, Python has built-in modules, and these other libraries have modules as well, right? So a module is a little bit smaller. It's a little more contained, and libraries are collections of those contained modules. So when you're talking about it, you know, pandas is not a module. Pandas is a library. And those semantics don't matter that much until somebody's like, hey, why are you using the word module for library, or vice versa. So let's see. One of the common ones, you know, common modules we use is math. So import math. There are a couple ways you might see this. If you're trying to take the square root of something, usually what I do, honestly, is I don't import math. I will just do, you know, 5. Let's say I want the square root of 24. I'll just do 24 raised to the 1/2. But I could also do math.sqrt of 24. And notice these get me the exact same number, the exact same result. If I wanted to import just the square root function, I could say from math, import square root. And on this line 6, I would no longer say math.square root. I would just say square root. And it works in the exact same way. This tends to be preferable. What I'm doing here on line 2, you tend to want to not import all of a module if you're only using one function from it. You know, so erring on the side of a little bit of simplicity, a little less code. Even though this looks longer, you're importing less code into your environment. Something else you might use a lot is factorial. We've written factorial a lot of times, and we're going to ask you to write factorial on the interview, most likely. So, you know, you could do this import, but we'd prefer you not. Well, you could, but we'd still ask you to write factorial. So, from scratch. But as you can see, this is just going to give us what, you know, factorial 5. You know, it's going to give us the same answer as we would have expected with a factorial function we write ourselves. So let's go ahead and look at the math library. This is all built in. We've got a number of helpful things like the ceiling of a number. That's like, you know, rounding but always up. We've got a combinations function. So we could use this. This just returns, you know, k, n choose k, right? Pretty simple. We've written that in Premium Prep a number of times. We're going to write it from scratch later. But know that it exists. It exists in the math module. And if you wanted to import it, you could just say, you know, from math import combinations. And you could do, well, what are the combinations of 20? Choose 7. $77,520. This is a lot easier than writing a combinations function from scratch, but I'm going to encourage you to write one of these from scratch and then use what's in the library after that time. Yeah, and there are a number of functions in here, right? greatest common divisor, right? Is close is kind of a cool function you might want to read about. There's a permutations function. There's a remainder function. There's e to the whatever, exp. There are also other things you can import, like you can import e directly from math import e, and you can then use e, right? Let's just print e first, and there we go. We get a value for e. This is one of those things. If you are going to write the Poisson function, the Poisson PMF, right? So let's define that Poisson PMF. We're going to expect you to be able to write this, and we're going to expect you to import e when you do it. So, from math import e is how you would do that. So lambda, and then let's put in a k value, and I'm going to just say return e to the negative lambda times lambda to the k divided by factorial, right? We need factorial of k. I'm just going to import factorial really quick. And let's print this with a lambda of 10 and a k of 10. And that's working correctly. But notice in this case we've imported a variable name, or we've imported an object which has a specific numeric value, 2.71828, etc. And we've imported a function. E is not a function. We could have imported exp, and then we could have used that directly as a function. But yeah, you can import the actual value of e. And yeah, there are a lot of functions in here, in different families of functions. So that's the math library. We actually are calling it the math module over here, but it's a library. After I explained already. Okay, so random. You're going to want to know about this function called choice. So from random import choice. This works really simply. Let's say we have some list, and I'm just going to put cat, dog, bear, weasel. If we want to pick from random from this, this is just going to be choice of list. It's going to pick a random element from this list, okay? And you would expect this to pick these elements in a random way that will give equivalent frequency to each if we were to do it over and over again. So we get cat, we get weasel, we get dog, we get bear, we get dog, weasel, etc. Just to kind of prove the point, I'm going to call out to this 1,000 times, and we're just going to count this to see if these counts are relatively even. So I'm going to say for sample in range, let's do 1,000, and we'll make a dictionary to collect this. We're going to say this is going to be, I don't know, results from choice, from the choice of the list, and we're going to say if the result is not in the dictionary, then we're going to do d sub result, and we're going to set it to 0, and then we're going to say we're going to increment it by 1, and this should show us a fairly even rate, right? We should see about 250 of each with some variance. So I'm going to say for key value in d.items, This is that common pattern that you're going to see everywhere. Oh, good question. Is it correct to say a library is a collection of related modules, and a module is a collection of related methods and functions? Yeah, I think that's a correct statement. And, you know, some of these built-in libraries are fairly trim, and, you know, we're not importing from math.trigonometry. We're just from math import something. And so they kind of look like modules. They kind of feel like modules. So I need to double check. It might be a misnomer to say the math module. I think it should be actually the math library. But math module might be correct there too. Anyway, so for key value and d.items, let's print again this familiar pattern, f string on the key and the value. And so we have, you know, it's not exactly 250, but if we run this again and again, and if we were to analyze this over and over again, we would see that this is reasonably random. Choice is reasonably random. So we can do from random import choice. Another thing we can do is from random import random. And let's just look at the result of the random function. So the result of random, and I'll just run this a few times. This is going to choose uniformly from values between 0 and 1. So what happens if we multiply this by 10? Right, we're going to get values between 1 and 10. And, you know, if I cast this to an integer, or sorry, between 0 and 10. Right, now we're getting integers in the range of 0 and 10. If we wanted to do between, you know, 1 and 11, we could just add 1 to this. But in general, you know, if you want to choose a random integer, it kind of makes more sense to use choice. And I'll just show you really quick what I mean by that. So we could use this int random times something approach, but we could also say we could print from the choice of the list of the range from a low value, and this makes this easier, right? Maybe between 15 and 75, 75 inclusive. So this is going to uniformly choose from values in the range of 15 to 75 inclusive. So when would you want to use random? If you want a value between 0 and 1, and you want that a lot, actually. That's it's something that you can get all the time. Oh, you know what? The other way that you can get a random integer is just with the randint function, which is randint. I always forget about this when I usually do that choice from the list of the range, but that's probably a little more computationally expensive. Not significantly, but yeah, if we want to get something between 15 and 75 inclusive, it would just look like this. So choice, random, and randint, random integer, right? Yeah, and if we run this a bunch of times, we'll see that we get these numbers uniformly as well. Yeah, so some special really effective things exist in the collections module. Counter is pretty helpful. It gives you a really quick way to count some things, right? So, you know, we've got a simple example here, and I'm just going to recreate that example. And then we'll look at counter. So, you know, I'll just get a random thing from Wikipedia. Just grab a paragraph. Okay, I'm gonna find a paragraph soon. I really want a better random in Wikipedia. That's just me though. Okay, so we're just gonna take this paragraph and yeah, there we go. All right, so we've got this paragraph. We can use you know, counter on this paragraph, and let's just see what this gets us. So I'm gonna call this D, and let's do for key value in D.items print, and same f string idea. Oh, whoops. So notice what this gets us. It gets us the letter frequencies and, you know, spaces, and there's probably some punctuation in here, of course. But what this has essentially done for us is it's given us a quick count of everything in there. Now, we passed in, you know, this sentence or this paragraph. We would probably prefer, well, we'd probably prefer a count of the words, right? That's something that would likely be more up what we're looking for, up the alley of what we're looking for. So instead of, so I'm going to do paragraph. What should I call this? Let's call this split. And I'll just go ahead and split this. And I'll split it on empty spaces. This is actually the default, what it splits on. I don't have to do that. But now, you might remember I wrote that, you know, a few days ago, if you were in class, I wrote kind of a cleaner and you know, a splitting, a counter. I essentially wrote a counter, a word counter. So let's see what this gets us. Since we're splitting on spaces, we're actually going to have some issues here, right? We're going to have shield as its own word, shield comma, and we'll see that. So remember that, okay, so the word not is uppercased here. If not exists somewhere else in here, it'll be lowercased. You know, we could do a little bit more cleaning of this. And why don't we do that, actually? So I'm going to do, I'm going to lower this first. So I'm going to do P lower. P lower is going to get paragraph dot lower. So I'll do that as a first step. And that should do a little bit better. I'm also going to want to clean out the punctuation. And I'm probably going to do this in a somewhat yeah, I'll just do it. So I'll just say I'm going to write over P lower, and I'm just going to say P lower dot replace, and we've got some periods in there. I'll replace those with empty spaces, and I'm just going to do kind of a stack of these. if you can't remember kind of how to do this in its own function or something like that, this is a way, or if you just want to write something really quick, this is just a quick way to write some of this. And then I think we've got an apostrophe in there somewhere, like that. Notice I am using the backslash to escape the apostrophe in there. So now when we do this, oh, what am I missing? I have an extra single paren. There we go. So now when we do this, well, we've got this 5 pointed, but I think this counts as one word. Phrygian. That's nice. Yeah, now when we're looking at this, we're seeing actual word frequencies across the entire length of this. So counter, really all this is doing for us is we can pass in a list, and it's just going to give us a dictionary of the counts without us having to write, without us having to iterate over the list directly in order to build this. That can be really helpful, and it's fast, it's easy, and it just looks like this. We're also talking about default dictionary here. I'm not going to get into default dictionary because we really prefer at this stage that you check for membership in dictionaries. All default dictionary really does is it allows you to not have to check for membership. So you could, for example, increment a value. Maybe I'll just grab this and point and just try to explicate what we mean by this. So in this case, we're getting a random integer between 1 and 6, right? This is a dice roll. Should this be 6 plus 1? Yeah, this should actually be 6 plus 1 if we're considering it to be a dice roll of a 6-sided die. But at any rate, we get the roll. We're not checking for membership here, but we don't have to because by default, there is a value for a key, even if that key doesn't exist, right? So here we're getting, let's say we get 3 on the first pass of this. It's going to try to increment something that doesn't exist, but it's going to intuit, it's going to impute that the original value here was 0, right? So it gives us a basis from which we can count. That's convenient, but it just really gets rid of a single line of code when you think about it. So if I were to rewrite this to just be a regular dictionary, I could say this roll gets a random int. I guess I am importing random. Okay, good. This is going to get, so see what happens when I try to run this. It says there's a key error of 4, and that's because 4 does not exist in here yet. So what I would have to do is check for membership first. So I'd say if roll not in the count dictionary, then we need to prime it to be there. So count dict gets 0, and then we can increment. Count dict sub roll gets 0, and then we can increment that value of 0 to 1. Using a default dictionary, we don't have to do that. But this works. Either way works, right? We want you to know how to do this for the technical interview. You can use a default dictionary for those problems, but make sure that you understand checking membership before you use default dictionary. At the end of the day, this code is going to get us to the same place. Notice this is of type default dictionary, and it's assuming that our class is integer, right? So you don't want to have mixed types in a default dictionary. But you know, at the end of the day, it's accomplishing the same task as this would if we were checking membership. And there's actually a lot in the collections module, or sorry, the collections library. Like we've got an ordered dictionary and oh, interesting, named tuple. I haven't used that at all. Anyway, you know, feel free to read through this documentation. This is old documentation. You probably want to use 3.7. Yeah, here we go. These are, you know, these are slight variations on the built-in data structures. You know, they can come in handy, but you don't need to know how to do these sooner. You can mostly write these from scratch if you need to. Yeah, there are a couple things here that are maybe a little more unique, like a chain map, those kinds of things. But you know, feel free to explore collections, especially counter. I find counter to be very helpful a lot of the time. So let's look at importing your own files. This is something that is going to help you keep your code clean. So let's say you have some procedural code here, right? Let me think about this. I think about this in terms of separation of concerns. If I have a bunch of plotting functions, I'm going to keep those in a different file from you know, code that is doing something, right? But in this case, let's just import something from, well, I have this thing open over here called Sudoku Solver. Yeah, let's get something out of here. Let's just generate an empty puzzle. So I'm going to say from Sudoku Solver, import, what was that called? Generate empty puzzle. So let's just print the result of generate empty puzzle. Even though I haven't defined this function in here, I've imported it from over here, which should allow me to generate an empty puzzle. This is just a list of lists, as it turns out. It's not presented in the most pretty way right there. I could just say for row in that, I'll print the row. Okay, so that looks a little more Sudoku-ish, right? Sure is printing a lot of rows. Not sure exactly why. All right. Something to consider with this, with importing from another file, is if you have code that's running separate from your functions, that code is going to run when you do your import, and that can be pretty frustrating. That can be pretty annoying. That's what was happening just now. Because I had these lines 228 through 232 running. So I'm importing a specific function called generate empty puzzle, but I could import everything like that. And that might be more what you're trying to do. Especially if you have a small project. If you're writing a function in a separate file, you're probably going to import every function in that file. I tend to only try to import the functions that I know I'm going to use. So, you know, if I'm not using everything in here, I would probably name each function individually. Yeah. You could also just simply do import Sudoku solver, and that would work as well, except now you have to prepend the you have to prepend the name that you imported to the function here. And I believe, yeah, we kind of went over this, importing specific functions. We already went over that kind of throughout all of it. Okay. So we're going to call it there today. Next time, we're going to get started on the prob stats materials here. So we just completed the last unit in intermediate Python, and you know, there's we already went through all of Welcome to Python, or Intro Python, that is, and now we're going to start on you know, Intro to Stats, and we'll go through all of this, and once we finish that, I'm gonna come back and you know, that'll probably take maybe a week and a half, maybe 2 weeks, and then we're going to start from the beginning of intro Python again. But remember, you can always ask questions from anywhere in the materials, and I'll address those questions in the study hall. Also, yeah, feel free to post your questions in DS Basic Prep or in the Premium Prep channel. And either someone on our team or more likely one of your peers will answer you sooner, right? And that's how we get unstuck. So you can bring your questions to Study Hall. You can also bring your questions to Slack, and we highly, highly encourage you to bring your questions to Slack at any time when you have them. There are, I think in the DS Basic Prep, there's something like 1,000 active users, and so only a small fraction of you are posting questions, but there are a lot of people there who are happy to answer. So yeah, keep that in mind. Yeah, that's it for me for today. Wednesday, same time, 4 p.m. Mountain Time, 3 p.m. Pacific, 6 p.m. Eastern. And Thursday, we'll either have a study hall at that same time, or I'll present on some data science or Python coding project. Either way, Monday, Wednesday, Thursday, Friday, we're streaming at the same time. So I'll see y'all really soon.